and we will hear about the experimental side.
Hi, can you hear me?
Yes, we can hear you, and we can.
And can you see my slides? Are they moving?
Yes, we can see it.
Okay, right. Okay, so thank you for the invitation. I feel like I'm filling in a sort of theorist sandwich here with Yuval before me and Gudrun after me. So I see my role is to elaborate on, give a bit more experimental context to some of the things Yuval said, and set the scene for Gudrun. So let's get going. After a brief introduction, I will discuss some recent results, including one very recent result. So watch out for that. These will be by nature rather selective. And I'd like to spend the last 5, 6, 7 minutes of the talk looking at the future of experimental flavor physics. So some confessions though. My discussion will be restricted to quarks and hadrons, though there's clearly plenty happening in the charged muon sector, which will be covered tomorrow. And unavoidably, my affiliation is with LHCb, but this is where most of the interesting results have come from recently. I had this rather pompous title, The Age of Flavor. What do I mean by this? Well, the Age of Flavor, I say, started at the beginning of the century, and these measurements, which were made by the B factories of time-dependent CP violation in J psi, K short, and K long, which confirmed the CKM paradigm as the dominant mechanism of CP violation in nature. This, of course, led to the 2008 Nobel Prize. And since then, a huge number of similarly exciting measurements have flowed out. And it's my contention that no other area of flavor particle physics has delivered such a rich and extensive set of results during this period. So we are living in the age of flavor, and I think it is continuing. So who are the heroes of this age? Well, there's the B factory experiments, Barbar and Bell. I'm sure you know about those. There's measurements made at charm threshold, initially by Clio C and now by BEST 3 in Beijing, which is still data taking. There were the Tevatron experiments, which made very, very important initial measurements in the BS and indeed in the charm sector. Then, of course, there's Atlas and CMS, which are very, very powerful detectors indeed. But clearly, most of the results which are coming out at the moment are coming from LHCb, which has this distinctive shape. It's this forward spectrometer. This collected 9 inverse femtobarns in the first 10 years of operation at the LHC. And the results I show today will come from this, though not all of these data have yet been exploited. And the experiment is now being graded for run 3 and run 4 operation, and I'll talk about that later. And we have a new kid on the block. We have Bell 2, and Bell 2 is rebooting the highly successful E ± B physics, B factory franchise. So it's continuing where Barbar and Bell left off, and the aim is to accumulate 50 inverse Atabarn, so that's 50 or more than 50 times each of these individual experiments collected before. And this will be able to perform measurements over a very wide range of topics. And its particular strengths will be in modes with neutrals and missing energy, so highly complementary to LHCb. I say will be able to, Bell 2 is taking data, it has been for some time, and the luminosity is gradually ramping up. So it's reached a record of 310 to the 34. That is still about an order of magnitude below what it's aiming for, so it has a way to go. And it's collected something like 175 inverse femtobarns. So it's still early days. But even with these early data, some very nice results have come out. So some sort of first sign to beta measurement. Of course, this is not competitive, but it's really nice to see this familiar wiggle plot emerging again from a B factory. Some hadronic final states and modes with missing energy in the final state, where this like B plus to K plus nu bar, where Bell 2 has really a lot to offer. So watch out for Bell 2, and I'll tell you later about the prospects. Okay, so now on to my list of measurements. I'm being selective here, and I'm going to start with some discussion about electroweak penguins, also known as the anomalies. Now, I'm aware that there's a talk scheduled tomorrow, an experimental talk, where you'll get many more details from Julian. But since Gudrun is talking about the theory of this afterwards, I think it's necessary that I give you some basic experimental facts. So these class of BS to L plus L, B to S L plus L minus decays, such as B to K star L plus L minus, they offer many observables which can probe the helicity structure and more of any new physics. So for a lot of these observables, you'll see plots against Q squared, which is the invariant mass of the lepton final state, the dilepton final state. And then you can construct various observables which are plotted against this variable. For example, the first favorite one was the forward-backward asymmetry. This is the forward-backward asymmetry of these the lepton system in the B rest frame. There were proof of principle measurements made at the B factories. You see that what's expected in the standard model is this characteristic asymmetry which goes negative through a 0 point and goes positive again. So with the rather limited data sets that the B factories had, there were initial signs that something very different was going on. But now with the data we have from LHCb, here almost all the data has been analysed, but there's still quite a bit to come from the last 2 years of operation. You see that this characteristic negative then positive forward-backward asymmetry is indeed seen in the data. But if you look more closely and compare with the predictions, you see that there is some tension. And that tension is happening at rather low Q squared. One could go further and make construct other observables which are not as easy to understand and have really horrific names, most famous as P5 prime. What this describes physically, I can't begin to explain, but it's constructed to be as robust as it can against form factor uncertainties and also quite relatable to the short distance physics. And you see on the left this problem which has persisted for since the analysis of RAN1 data and has remained and been seen in new data sets that again you have a difference which is seen at the low Q squared. And this difference is in the 2.5 to 3 sigma regime across those bins. But there is a word of caution. The standard model uncertainties here are from one group, others are available, and you can hear lots of discussion about whether these uncertainties are fair or not. And there have been measurements by Atlas and CMS, which Atlas go in the same direction, CMS less so, Bell also, but really the statistical precision of these other measurements is not yet adequate to really provide elucidation. Now, if you step back from these really odd observables and look at the simple things like the differential cross sections, here the theoretical uncertainties are certainly larger, but what is striking is that across the whole family of decays, all mediated by the same underlying quark process, you have a discrepancy. You have a discrepancy in the low Q squared region. It is definitely there. So again, because of the theoretical uncertainties which are here, we can't read very much into this, but it's interesting. And the measurement at the bottom left for BS to phi mu mu, that is a new measurement. Something important to realize is that all the studies which you've seen from the LHC have been performed with muons, all the studies I've shown you so far. All these on this page and all the ones on the previous page. So this is one motivation to try and look at results with electrons and try also to construct some observable which is theoretically clean, which is pristine. And this is these motivates the lepton universality tests, where essentially in a bin of low Q squared, we actually measure the rate of the dimuons divided by the rate of the dielectrons. Of course, this should be 1 in the standard model. And there's lots which goes into the measurement to try and make this as experimentally robust as possible, and you'll hear about that tomorrow. But let me just flash the results in their simplest form. A measurement has been made of beta KL plus L minus, that's the top one, and that uses all of the RAN1 and RAN2 data. And the bottom one is made with beta K star L plus L minus. And in both cases, we have a measurement which is below the standard model by a significant number of sigma. So this is very, very intriguing indeed. And the theory prediction here cannot be questioned. So what this means, well, Gudrun will tell you that. I just make three very brief points. Yuval seemed skeptical. He said this was ugly, but I think the wider community tends to think that what's appealing is that when you look at all of these anomalies together, what's nice is they seem to be rather consistent. Something strange is happening. That strange thing is coming predominantly from the muon sector. How much disagreement you think there is depends on which of these observables you add into your basket and whether you privilege the theoretically clean lepton universality violating ones. But from an experimental point of view, this is not the end of the story. There's more results to come from LHCb, some very important ones. For example, the measurement of RK star with the full data set and looking at these P5 prime and related observables with electrons also. Let me now turn to CP violation and CP violation in the B sector. I want to just focus on this unitarity triangle Yuval showed us, but on one very specific part of it, and that is this angle gamma. So at LHC turn on, this was very badly known. The CKM fitter uncertainty was more than 20 degrees. Now, the predicted value of this, it's not something you can predict from the vacuum in the standard model, but you can predict it by the structure of the unitarity triangle and all the other constraints we have. And the predicted value is this, 66 degrees, with an uncertainty of about plus or minus 2 degrees. So this predicted value depends on other measurements which involve loop level processes, and these could easily be affected by new physics. Now, the best way to measure gamma, so we want to make now an actual direct measurement which we can compare to this. And the best way to do that is to look in processes such as B to D0 K and B to D0 bar K, and we look for a mode which is common to both D and D bar. This provides interference, and this gives you sensitivity to gamma. So here's one example, a very simple one, but a very famous one. So this is where D goes to K pi, and the charge configuration is such that the kaon from the D is of different sign to the kaon from the B. This has a very rare visible branching ratio, very suppressed 10 to the minus 8. So it was really out of reach for the B factories. But with LHCb, this is now the complete data set. You see the precision is beautiful. The decay is seen on the right, it's in white, and you see it plotted separately for B minus and B plus. So you see the peaks are of very, very different heights, and this is CP violation. People say CP violation is a very small effect in the standard model. It's tiny in the kaon system. If you look at things like this, it's enormous. And what's more, this CP violation can be cleanly related to the phase gamma. So you can go further, again looking at these B to DK decays, and you can look at multi-body decays. So for instance, D goes to K short pi pi. This is a relatively recent measurement. And what you do here is not look at the absolute rate, but you look at the phase space of the D decay, which is plotted here. These are so-called Dalitz plots of the D decay, but plotted separately for B plus and B minus. So you see the rich resonant structure giving the varying density in the Dalitz plots. But again, if you compare B plus and B minus, you see there are differences. Here are some. So this again is driven by CP violation. Now, to understand these differences and actually turn these into quantifiable measurements of gamma, we need to be careful. What we do is divide the Dalitz plot into bins, and the bins have these unusual shapes which you see on this plot on the right, sort of ink blot like a butterfly plot. And these bins are chosen because in these bins, the actual strong phase variation across the Dalitz plot is rather similar within a bin. But we need to know what this variation is within a bin of the strong phase. And this is where the LHC cannot cope on its own, nor could the B factories. We actually rely on external input, and this is a very beautiful example of the synergy of experiments. We actually measure this input, that is the strong phase values or the cosine and the sine of them you see in this right-hand plot here, from quantum correlated DD bar events, which are available at BESS3. So these were recently made available, and the precision is just right for the current LHCb measurement. But moving forward, we would like more precise measurements. So it's very important BESS3 keeps on running. So if you make sense of all this, so on the left here, this is essentially the difference between the B minus and the B plus populations in each of those bins, and then a fit is superimposed over that, which varies strongly from zero being no CP violation. And this fit enables us to extract gamma. We see we measure gamma with a precision of 5 degrees. This is the single most precise determination of this quantity. This is not yet included in a combination with all of the other D decay modes of this to D decay chain, but an earlier average yielded 4 degrees. So one can anticipate that when this combination is made and all of the run 1 and run 2 data are analyzed, we should have a precision of something like 3, maybe even 2 degrees. So this is remarkable progress, 10 times better than when the LHC was turned on. The central value is in agreement at the moment with the indirect prediction, but still we are not as precise as we would like to be. So we need more data, and this will be a common theme. Let me skip over these 3 slides and then move on to the next topic, which is a discussion of charm. So this was introduced very nicely by Yuval. And what I would say is that this age of flavor we live in has seen a renaissance in charm studies. Yuval focused on the CP violation, which I'd very much like to have talked about if I had more time, but I'm going to focus on the mixing, because here there's a beautiful new result. Now, charm oscillations are slow, and they are mediated by these 2 parameters, X and Y, related to the mass splitting and the width splitting respectively. And these are essentially impossible to predict in the standard model. All we know is that they are small, and for a long time people thought they were going to be unmeasurably small. So, but for many, many years, for decades, people have been looking for evidence of charm mixing, but nothing was seen. So on the left, there's a plot of X against Y, and these are the excluded regions. So back in 2006, nothing was seen. All results are null, as my colleague Ian Chipsey said. But then with the analyses coming in from the B factories, the situation very rapidly changed. And only 1 year later, one could say with confidence that mixing exists in this system. Okay, so this came from not a single measurement, but a combination from a whole load of measurements from both Barbar and Bell. So this was very, very rapid progress. So we made even more progress since then. So if you look at the rightmost plot from last year, you see we now have the actual data lie millions and millions of sigma away from the no mixing hypothesis. But if you look at the axes, you see that Y is quite well measured now, but X, this parameter related to the mass splitting, last year there was no definitive proof that X is non-zero. So this is where a new result, which became public not just 1 week ago, changes things. So we go back to this decay, which we already exploited in the gamma measurement, K short D to K short pi pi, and now we just look at it for its properties in charm studies. Again, its rich resonant structure is very advantageous for mixing and CP violation measurements. The new result, which LHCb's just released, exploits essentially all of the run 2 data. And this is, you see the plot, the mass peak on the right. This is 31 million decays. See, it's incredibly clean. And this 31 million is something like 30 times the samples available at B factories. So again, as in the gamma analysis, we divide the plot into bins. This is a very slightly different binning, but the strong phase characteristics of these bins are known from the best 3 measurements. We then compare the ratio of the populations in symmetric bins. We call this the bin flip method. It's particularly sensitive to X, and we study these ratios as a function of proper time. There's lots of experimental details which are important, but we don't have time to dwell on these. I'll just go straight to the result. So on the left here, for the 8 pairs of bins chosen, for each of these bins you see a ratio R1 through to R8. These ratios are plotted against proper time, and you see that these ratios vary with proper time in a manner which is, if there was no variation, if these lines were flat, there would be no mixing. But there's clearly mixing happening. And this measurement is very much sensitive to mixing driven by X, the mass difference, rather than Y, the width difference. The numerical result is at the top, but let me just, if you focus on the plot on the bottom right, what you see is now X is clearly lying a long way from zero. So this measurement has told us with a significance of 7 sigma that X is non-zero. So this is a big step forward. Just to show you how big a step forward it is, we can superimpose this measurement. If you look on the left plot with, we can look at the current world average, essentially the plot I showed you a few slides back, and then you can superimpose how this changes with this, this new measurement added. So a big step forward. On the right plot, you see the consequence for CP violation studies. These are CP violation which are related to mixing phenomena. So there's 2 parameters describing this, one on the x-axis, one on the y-axis. The plot is constructed so that 0, 0 is the standard model, but you can just see this enormous step function in our knowledge that this result has made. Looking forward, now that we know that x and y are non-zero and also significantly larger than was once guessed, this gives us great encouragement to move forward with these CP violation studies. There's real hope that by the end of the LHCb operation, standard model value could even be within reach, and hopefully we'll see something before then. I included 2 slides on kaons, which I won't dwell on, but this is just to talk, this is just to acknowledge the continuing importance of kaons in flavor studies, particularly picking on these very rare modes, K+, the pi plus nu bar, pursued by Na61, 62, I beg your pardon. And one sees that the precision, I mean, this decay is at the 10 to the minus 10 level, but it's now seen with good evidence by Na62. And within the next few years, they hope to attain a 10% precision. And then there's the neutral counterpart, Koto, K0 long, so K long to pi 0 nu bar, which has been pursued by Koto. This is suppressed by a factor a third with respect to the other one. And so it's going to be a long road to get there. As Yuval mentioned, some data were analyzed and released last year, and a few events were seen, but these were understood to be explained by background, which was not foreseen in the initial analysis. But these things happen, and as a consequence of this, the upcoming data collection and upcoming analyses will be adjusted to fight and combat these backgrounds. Let me spend the last 7 minutes, I think, of the talk just talking about the future of flavor measurements, and this with a focus on the collider experiments. We should come back to Bell too. So this is the latest plot I could find of the anticipated luminosity increase. So shutdowns are foreseen, one in 2020, 2 to install laser the pixel detector, and then a later one in the middle of the decade to upgrade the interaction region, which will allow the luminosity to be substantially improved. So the tentative forecast at the moment is that this 50 inverse antibarns should arrive around 2031. And to put this in context of the measurements we've spoken about, for instance, the anomalies, one sees that this means that by 2023, they should have sufficient data to be able to match the precision of the LHCb run1 P5 prime measurement for muons, but very, very excitingly for electrons also. So even if this measurement P5 prime has a theoretical contamination, if you compare it between electrons and muons, that will be a very, very powerful test of the standard model. And if the central value of RK is true, they should be able to get a 5 sigma measurement with 20 inverse attobarns, which would arrive around 2028. This BEST 3 program, which I spoke about and is very important and can do a lot more than I've had time to actually discuss. BEST 3 continues to run, but there are proposals for experiments, so-called Tau charm factories, one in China, one in Russia, which would essentially be BEST 3, but running at something like 100 times the luminosity. And these would be foreseen for the end of the decade. So this is something we should really, really hope comes to pass. And now back to LHCb and the progress that is foreseen here. So this is a plot of the various runs of the LHC from the startup and run 1 through to run 6 in the middle of the next decade. I should say at the outset that this the actual long shutdowns in the starts of each run you see here are not quite correct, and that's because the LHC schedule was adjusted about a year ago, and I've not yet updated this plot, partly because I think the schedule will be updated once more. But the general features you see with respect to LHCb are correct. So we had the original experiment, which collected this 9 inverse centibarns, about 3 inverse centibarns of which was at half the design energy. What will happen next is what we call upgrade 1. So this is going to increase the operational luminosity by a factor of 5. And even more importantly, the trigger is going to be completely overhauled. The hardware trigger is going to be removed, and we're going to trigger the entire experiment just using software, using CPU. This means you have much higher efficiency for tricky modes, and you have much more flexibility. So this will bring great opportunities. And the idea is to operate this experiment throughout run 3 and run 4 and collect 50 inverse centibarns. So in total, more than 5 times we have now. And for certain channels, the event yields will be much larger because of this new trigger operation. I say this is a plan. What I wish to emphasize is this upgrade is essentially now. It will be a new experiment, and this experiment is being installed, as I speak. So here's a few highlights. One sees on the right, for instance, this is what you're looking at here are planes of MAPMTs. These are photo multipliers used to detect the rich rings. This is one half plane of rich 2, and it's fully equipped. On the bottom, you see one of the new tracker stations for the sci-fi being lowered down into the cavern and being installed. And on the left, you see progress with the Velo modules. So this is an experiment which is almost upon us, and it will begin data taking at the start of next year. But this will not be the end of the LHCb program. There's now plans for an upgrade 2, which would increase the luminosity by something like a factor of 10 with respect to now. When I say now, I mean original LHCb. And this is the highest luminosity we could possibly reach in our interaction point. So this is a very interesting challenge. And it's one where a lot of work is invested already. So these are documents you can read. And now a so-called framework TDR, a technical design report, is being written to be submitted to the LHCC this autumn. There are many fascinating detector challenges, for instance, overcoming the high radiation environment and using very fast timing, very precise timing to try and associate decay vertices with the right primary vertex. So we're having a lot of fun planning this, but we welcome new collaborators. So if you are feeling idle or you feel motivated, please come and speak to me or one of my colleagues. So this is one of the plots that Yuval showed you at the start of his talk. This is a plot which was made essentially with the current knowledge, so it's actually the 2018 knowledge. This is using only LHCb inputs plus lattice QCD inputs, which are very important. This is how things will evolve. Again, just with these inputs, looking towards the middle of the decade when the LHCb upgrade 1 has run half its course. And this is the situation we might anticipate after upgrade 2. Again, just with LHCb and lattice inputs, you see the increase in precision is remarkable. Of course, I've lined things up here, so in strict accordance with the standard model and CKM paradigm, but we very much hope for deviations from this. And finally, in the last 2 slides, I want to look even further forward, what could happen in the 2040s. So you will have heard of the FCC, the Future Circular Collider. It will eventually be a hadron machine if approved, but before then it will have an E plus E minus phase. And this FCC-EE is was proposed initially for doing Higgs studies, but the energy is variable. So you see right in the middle of this plot, 250 GeV, this is the HZ production, this is the Higgs working point. But a characteristic of a synchrotron is that the energy falls rapidly with, the luminosity falls rapidly with energy. So one has the choice of actually going downwards in energy back to the Z pole, and the consequence will be that the luminosity will rise enormously. So you get a total luminosity of something like 5×10⁻36, which is colossal, and this is something which would not be available at a linear collider. This is just something you get for free because a synchrotron has this characteristic dependence of luminosity on energy. And this would give you something like 5×10⁻12 Z0s over a 3 to 4 year period. This has great potential for electroweak physics, but also for flavor physics. You'd get something like 10⁻12 BB bar pairs. You get them in a clean environment. You get all of the B species like at LHCb. You get boost. So this looks like something like the Bell 2 environment, but 30 times more, and you have all of these hadron species. So this will be very valuable, particularly for channels involving neutrals and missing energy, and for those involving taus. And here's a publicity plot of the peak you could expect for B to K star tau plus tau minus, which is very, very, very difficult to do at LHCb, and pretty much impossible at Bell 2 because of the statistical challenges. Here you would have many events to play with. Okay, I've come to the end of my time. Again, I think we're living in the age of flavor. The last 20 years has delivered a rich and extensive set of results. The measurements are important because they address many of the open questions of the standard model, and they are intrinsically sensitive to high mass scales. The results now emerging, particularly those from the LHC, are remarkable in their precision and in some cases very intriguing. And Run 2 still has a lot to tell us. The program is ongoing. Bell 2 and the LHCb upgrades will bring a great leap forward in precision and will make new observables accessible. So I think we are indeed truly living through a golden age of flavor. Thank you for your attention.
Thank you very much for the great overview talk. We do have a couple of questions. The first one is about RK and RK star. It says, we prefer to measure RK and RK star in low Q-square bins, not in high Q-square bins. So why is that?
Right. It's essentially pragmatic because it's experimentally easier. There's backgrounds and problems measuring them in high Q-squared bins. Now we would like to measure them in the high Q-squared bins, and there's ongoing efforts to do that, but those measurements are not yet available. From a theoretical point of view, the reason is just pragmatic. It's just easier to do it that way, but we hope to do it at high Q-squared as well.
And then we have a second question, which says, we measure observables in bins and not at specific Q-squared. Why is that? So I guess, are there prospects of doing some unbinned fits and stuff like that?
Right, no, there are actually unbinned analyses for these angular observables. There have been unbinned measurements made, and they will continue to be made. But I think bins are easier. When it comes to these RK observables, I think it's probably necessary to do them in bins. But I don't think there's again, it's an experimental reason. It's not a theoretical reason.
And then we have another question in the context of the rarity case. So let me just read that out. In the age of flavor, sometimes observers have been popular to then naturally fade to the background. Regarding the B2S and LD case, I vaguely remember that there was a time where there was interest in CP asymmetries and isospin asymmetries in the rarity case. Is this interest in this observer still alive? Maybe even with electrons? Or is that in the shadow of the RK and P5 prime?
No, I think all of these are of interest and are still alive. Yes, isospin observables isospin asymmetries were very fashionable for a while because there were hints of isospin asymmetries from the B factories, I think, and we had some hints with early LHCb measurements, but they evaporated. But I think we want to measure all of these things. The more we measure, the better. The convener of the session, the chair, can tell us more about that, I'm sure. or the next speaker.
And then one final question. How much will BEL2 be able to improve the LHCb CP violation results shown today? With the attention to the anomalies, are Atlas MS planning to enlarge their flavor program when the LHC restarts? So I guess two questions here.
Yes, yeah, and these are, the first one is actually quite easy to answer, I think. So in terms of the B physics CP violation measurements, yeah, BEL2 has a big role to play. It will make a very good measurement of sin 2 beta, which I've not talked about. So LHCb hopes to continue to make good measurements of that. But if things work out well for BEL2, they should be probably world leading in that. For gamma, they should do well as well, but I think quite not. But they will struggle to match LHCb. In terms of the charm physics, I think it will be tough for BEL2 because they just do not have. I mean, it's not because we're smart on LHCb. We just have so many charm events. So I think that will be difficult. As regards Atlas and CMS, I should apologise to my Atlas and CMS colleagues. They've already made very nice contributions to the B physics programs in terms of BS to mu, very important measurement, and also phi s, which are some of the slides to do with CP violation in the BS sector, which I didn't speak to, but they are there in my presentation. In terms of the contribution to the anomalies, well, they've already made proof of principle measurements. Whether they wish to enlarge their flavor programs, I think they are thinking about that, but it's not for me to say that you know, we should wait for an Atlas or CMS person to tell us what they're planning to do.
All right, excellent. Thanks again for the